Hey guys, Mr. Smith here, and in this video lesson, we are talking about transformations of the sine function and the cosine function, looking at more involved graphs that apply more than one transformation, and then using those graphs to try to model some real life scenarios. Lots of things in life are periodic. The example at the start of your chapter here talks about the volume of air contained in your lungs as you kind of breathe in and breathe out in a normal rhythm. But so many things are periodic, a pendulum in physics, a lot of biological rhythms, and having a good understanding of periodic functions can help you model a whole bunch of interesting things in real life. In our first lesson, we reviewed some of the basic transformations for the sine and cosine function. Let's review those transformations and which property they affected, and just get a little summary here. So we know that the parameter a, when we multiply a function by a value out front, it corresponds to a vertical stretch or compression. Depending on if a is the size of a is bigger than 1 or less than 1. And I'll add a second note here. If a is negative, there is a reflection in the x-axis, a vertical reflection there. And I think, you know what? I think I can work with a font size that's just a little bigger. Oh, that's the spacing. Where's the font size? There's the font size. Let's go 16. Okay, that should fit pretty well, I think. All right, and of course, what property is affected when we stretch or compress a periodic function? It is the amplitude that is affected, the amplitude. And as usual, as I'm shooting this, or I might have to pause once or twice if my office mate comes in. All right, let's talk about C, adding or subtracting a number on the end. So of course, we know that corresponds to a vertical translation. Nothing new. How much to add there? And what property is affected when we take a periodic function and we just shift it up or shift it down? It changes the axis of the curve. What we're kind of getting at is that when we have an equation and we want to graph it, or we want to come up with if we have a model and we want to actually model with or some application we want to model with an equation, the things we are concerned about is the amplitude, the axis, the period, the phase shift, and each of these corresponds to one of these parameters. Let's continue. So the value of k, so we know from our grade 11 course and reviewing this here, this corresponds to a horizontal stretch or compression. And if k is negative, there is a reflection in the y-axis. And of course, if I compress a periodic function horizontally or stretch it out, the property that that's affecting is the period. And I might actually just toss in a couple extra notes while I'm thinking about this, just a little improvisation here, so I can go into this one. So if the property that's affected by the parameter a is the amplitude, well, what actually is the amplitude? I can actually write this one in. The amplitude, if you're reading off an equation, the amplitude equals the absolute value of whatever the a value is. You can read the amplitude right from your equation. In this case here, the axis is y equals c. So you can read that right off as well. The period would be, you guys did develop this in your grade 11 course, but let's say that k was 2. So we know from earlier that when that value is 2, or a number that's 1 or above, we get a compression, and it compresses by a factor of 1 over the k value. So if we want to get the new period for a given k value, what we do is we take the old period of the original sine or cosine function, which is 2 pi radians, and we divide it by the k value. So for example, if k was 2, the function is compressed by a factor of 1 over 2, which takes the period, which is 2 pi, and it divides it in half to just pi. Lastly, d corresponds to a horizontal translation. And we call this the phase shift. That horizontal translation, that horizontal shift, we call that a phase shift. And the phase shift is just simply whatever d is equal to. The phase shift equals d. So what we're going to do, and I believe that the next few examples we do are going to be, it's basically a review of grade 11 stuff. It's just that we're going to be talking about the period in terms of radians. And on our graph, we'll be graphing with the horizontal axis is radians and not degrees, but it should be hopefully just review for you guys. We're going to graph some sine functions. We're going to graph some cosine functions. So generally I like to, on a lesson sheet or an assignment, provide you guys a grid just to make it easy. When you guys are doing your practice, the assumption is, you don't need to have graph paper, but when you're making a rough sketch, you'll take a bit of care and you'll label the key points, and or use Desmos to kind of check and answer. But yeah, like while we're doing a lesson sheet, I just like to have a neat graph. So in our notes, at least, we can have like really crystal clear graphs. And I've kind of outlined the strategy that I use when I teach transforming sine or cosine functions. And we're going to use this strategy to help us graph some more complex sine and cosine functions. So let's continue. So this first function is clearly a transformation of the sine function. And I've added a dotted line there representing the basic sine function. So let's actually just like pick off all of our properties. So first of all, we know our sine function goes above and below and kind of hovers above the axis. Where is the axis here? We can actually just read it from the equation. The axis here is y equals -1. There's a shift down of 1 unit. Our axis of y equals 0 is shifted down to y equals -1. My advice is to graph that right away. So I'm just going to do a dashed line. Okay, next, what's the phase shift? So the phase shift here, we can see it's x plus pi over 2. So we know that's a shift to the left of pi over 2 units. So the phase shift, so you can think of d here being negative pi over 2, which means we're going left by pi over 2 units. So the next thing I want to do is talk about, okay, I use this term, where am I going to start my sine function? So look, normally the sine function, I'll erase this in a second. Normally our sine function starts at 0, 0, and it goes up from there. We're shifting our graph over by pi over 2 units. So our graph, the one we're transforming, is not going to start at 0 and then go up and come down. It's going to start at pi over 2 to the left and go up and come down. So we're going to start on the axis and not at 0, but at pi over 2. This is where our sine function is going to start. What's our period? So our period, since k is 2, our period is going to be 2 pi divided by k, which is in this case 2. Our period is going to be pi. So we know the basic sine function starts at 0, 0, and every pi radians, there's another x-intercept that comes back down. Well, if the period becomes pi, then everything gets squashed together by a factor of half, and it takes one full cycle. One full cycle happens in pi radians. So if I go over pi radians on my scale here, pi radians is 6 of my little ticks. One complete cycle would get me to here. So what I've suggested is plot the x-intercepts, or where we hit the axes, every half period. So we know that one full cycle will be pi radians. So every half cycle, our sine function comes back down, right? So every pi over 2, we know we're going to be coming back to the axis, so we can fill in that detail on our graph. And actually, sometimes I just put a little SP so I don't lose track of where my starting point is. And now we're ready to use the amplitude to finish our graph. What is the amplitude here? We can just simply read it off. It's equal to 3. So what that means is, for our amplitude, we're going to be going 3 units above the axis and then 3 units below the axis. So I think I might switch up to a different color here. So from our starting point, between these two, where we come back to the axes, we're going to go up and come back down. So halfway between there, we're going to reach an amplitude of 3 units above. And then between these two guys, we're going to be 3 units below that, down to -4. And this is basically one complete cycle of our function. And we're just going to fill up the graph with more points. 3 above, 3 below, 3 above, 3 below. I guess with the shortened period, we're definitely going to fit a lot of cycles on here. And that's okay. Up, down, up, down, up, down, up, down, and down, up. Okay. So our first sketch, this process generally works good every time. Plot the axis. Think about where you're starting using the phase shift. Use the period to plot all the points on the axis where we come down every half period with the sine function. And then use the amplitude to plot your maxes and mins. You get a lot of nice points. You can draw a nice graph. Now, I do have Desmos loaded up here. Let's have a look. I have changed my axes to be intervals of pi over 2, just like my graphs on the lesson sheet. So we do that by just making the step pi over 2. And so let's have a look at this graph. It is 3 times y equals 3 times the sine of 3 times x plus pi over 2 plus pi over 2. Close this bracket, and then -1. All right, and so if we have a look, looks like we did a pretty good job. You can compare everything. Maybe you could even draw in the axis, -1, just as a little visual. And yeah, looks pretty good. What does our lesson sheet go to? Our lesson sheet goes to just like 2 pi. Oh, I did 3. I was like, I'm kind of thinking to myself, I'm saying it looks pretty good, and I'm like looking at my graph. I'm like, oh, it doesn't look the same. That's because I put in 3 here. Okay, that's a lot better. All right, yeah, so pretty cool. So these steps will work every time. Let's do another one together and work through using this process. So step 1, where is our axis for this one? We can read it off. It's at y equals 1. Let's add it to our graph. We know our transform sine function will go above and below this axis. All right, where are all the points on the axis? Well, let's use the phase shift. The phase shift here, since d is equal to positive pi over 6, we know that the phase shift is right by pi over 6 units. So when the sine function normally starts at 0, 0, we're going to be starting here. We're going to move right pi over 6 units, which is like 30 degrees, which would be corresponding to exactly 1 tick on my graph here. So right there. And okay, so I'm going to just put a little SP. That's my starting point there. All right, And what's my period? So I can add more points. So here, our value of k is 0.5, meaning our period is going to stretch by a factor of 0.5, and it's going to stretch by 2 pi divided by 0.5. We get 4 pi. So the period's going to be 4 pi, which means every half period, 2 pi, we're going to be coming back down and hitting the axis. So let's draw that in. So every 2 pi, we're coming back down the axis. Every 2 pi corresponds to 12 squares on my graph. And then I'll go back 12, and then I would be here. And that's where we're going to come back to our axis. It's very, very, very stretched out. What's our amplitude? Remember, guys, our amplitude cannot be negative. So when we see the negative there, our amplitude is not -1. It's the absolute value of -1. So our amplitude here is 1. So our amplitude is not really changed. But do note, because this value is negative, whereas the sine function usually starts going up and coming back down, because of the negative, we're going to start going down and coming back up. So I'm just going to add a little note here that negative implies we're going to start moving down. And let's do that and add our maxes and mins. So we are going to we're going to be going down first, and we'll reach a minimum 1 unit below the axis, halfway in between these. So that's going to be 6 ticks, halfway right there. And then another 6 ticks back right here. We'll be going 1 above. And that's really all the key points that we can squeeze on here. So something like so. Yeah, it looks pretty good. Let's load up Desmos and have a look here. You know what I'm going to do is I'm going to change my y-axis just to make it look more like my sheet. It's 5 to 5. Okay. So our new axis is 1. And our new function, y equals negative sine 0.5 x minus pi divided by 6. Close the bracket, and then plus 1 was our axis. All right, so we come back to the axis at 7 pi over 6, 0, negative 5 pi over 6, 2. Looking at our lesson sheet, everything seems to be fitting pretty well. So it looks like we did a pretty good job. All right, so hopefully this method of sketching a periodic function kind of jives with what you did in your grade 11 course. Obviously, we all come from different spots, but more or less it should use kind of similar ideas. But this works for me. So we've graphed 2 sine functions now. Let's get an example in graphing a cosine function. So we should all know what the basic cosine function looks like. I've, as a courtesy, added this as a dashed line on our grid here. But the process for plotting a cosine function is much the same, with a few minor tweaks. So the things we can still read off the axis. Here, again, plus 1. So we'll put a dashed line at plus 1. Okay, there we go. What's our phase shift? So it's another pi over 6 to the right. Since d is equal to pi over 6, we know we're moving things right. Pi over 6, or 30 degrees, which corresponds to 1 single tick on my graph here. The period. Okay, so guys, because period is 1, the period of our transform function here is unchanged. The period will still be 2 pi. And it looks like our amplitude we can read off is going to be 3. But how do we sketch a cosine function? So normally the cosine function starts at a maximum. It starts at 0, 1. And so our cosine function is going to start at a maximum too, but not at 0. It's going to start at pi by 6. And it's going to start at a maximum, which is 3 units above the axis. This will be our starting point. So we've used the phase shift and the amplitude to determine where that first maximum is going to be. This is what we do for the cosine function. Now, in this case, I like to use the period and plot, okay, well, where else am I going to have a maximum? So the period's 2 pi. So another 2 pi units, I'll have a maximum. And going back 2 pi units, I'll have another maximum. So we've got our maximums. With the cosine function, I next like to add in the minimums. Well, where are the minimums going to be? Well, the minimums will be halfway between the maximums. And they'll be 3 units below the axis. So here, and then 3 units below, and then here. Where are we going to hit the axis? Well, we're going to hit the axis halfway between a max and a min, which would be, in this case, every 3 squares. So here, here. Can I fit another one on? Not quite, but it would be here, 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 and here. And we got a lot of nice detail for this graph. Down, up. Didn't quite pass through that one, but that's okay. Good enough. You guys show me when you're doing this process, you guys show me all those points. I can forgive you if your drawing skills lack. I don't have an artistic bone in my body, so yeah, I missed a few points there. That's okay. Hey, let's bring up Desmos and let's see how we did. So we're doing this time. The axis, I think, is still 1. It is, yeah. So our function, y equals 3 times the cosine of x minus pi divided by 6 and plus 1. Okay, so we had that maximum at pi over 6, 4. And it looks like we fit 3 cycles into this guy. Our lesson sheet fit 3 cycles. Everything seems to line up pretty well. I'll remove cosine there. We had, let's just add on cosine x. Sine's still hanging around there. Okay, so the one difference when graphing a cosine function, when you're thinking about where to start your graph, remember that cosine starts at a maximum. So we're using the axis and the amplitude and the phase shift all combined to figure out where that starting point was. And in our case, it was at the point pi over 6, 4. Pi over 6 units to the right. Use the amplitude 3 units above the x-axis. Okay, so 3 examples in the books. Let's get some experience making an equation. And then we'll just continue to graph, do a lot of examples today, get a good feel. All right, so in this question, we're going to be doing another cosine function. Our cosine function has an amplitude of 4, a period of pi, a phase shift of pi over 3 to the left, and a vertical translation of 2 units upwards. So we're going to determine the equation. We can pick off all the properties from there, and then we'll graph the function. If you honestly, I believe that many of you guys will be fully capable of doing this question without me. If you want to just try it on your own, let the lesson play, or just like mute it and carry along, and you do what you need to do. But yeah, let's just pick through things here. So amplitude of 4. All right, amplitude is 4. And I've kind of prompted you here. If the amplitude is 4, that's our value for A, right? We've got it. The period is pi. Okay, so the period is pi. This is going to help us find K. So how do we find K? Well, actually, let me rewrite. I might just rewrite this. So the period is always equal to 2 pi over K. What does that mean if we're given the period and we want to find K? Well, if you rearrange that, K is 2 pi divided by the period. And in our case, that's 2 pi divided by pi. So our value for K is going to be 2. So that's how you guys can find the K value. Divide 2 pi by whatever the period is. So we now have A, we now have K. What's the phase shift? So our phase shift is pi over 3 to the left, which means the D will be negative pi over 3. In our axis, we have a vertical translation of 2 units upwards. It's basically telling us our new axis, instead of being at 0, is going to be at y equals 2. So we can build our equation. Amplitude is 4. We are doing a cosine equation for this one. Our k value is 2, brackets, and our shift is left pi over 3. So x minus negative pi over 3 corresponds to x plus pi over 3. Close the bracket, and then our axis is 2. Now, what I want to say too, I know that the text practice has some questions where you're given a graph and you have to create an equation. You can use the same process from a graph. Like if I just gave you guys, for example, if I just gave you guys this graph here, right? You can read off the amp. Well, if you had a hard time seeing what the amplitude and axis was, you can just see, well, in this graph, the max is 4 and the minimum is 2, negative 2, excuse me. And so you can get the amplitude by doing max minus min divided by 2. You can get the axis by averaging 4 plus negative 2 over 2. You can get the period just by looking at the graph, and you get the phase shift by asking, okay, well, this is a cosine function. Where is that first maximum? And here it's at pi over 6. So you can do questions just like the one we're doing here, except instead of having a description of the transformations, you might actually just have a graph. Do the same thing, guys. Use a table like this, pick off all your properties. That helps you get the parameters, and you can make the equation. And now let's finish off by sketching. So we'll kind of move through this one using our process, perhaps a little bit faster. Feel free to pause the video if you want to just try it and work and just try it on your own before I kind of spoil the fun. But our axis is at 2. Okay. Where's my starting point? So my starting point is our phase shift is left pi over 3, which is 60 degrees, which on my grid is like 2 ticks. So it's a cosine function. So I'm going to start, my first maximum will be left pi over 3, and it's going to be 4 units above. I just realized I'll change this for your lesson sheet, guys, when I post it, and make sure you guys can fit that above there. But it's not a huge crazy deal. And our period is pi. So every pi, we're going to come back again to that maximum. So that would correspond to, on my graph here, every 6 squares. And that would be here actually too. Looks like we're getting a lot of cycles on this one. And 6 squares would be here. Okay, we reach our minimums halfway between those guys, 4 below the axis. So halfway, 2, 3. Oh, I think I need to move that guy over one more. Definitely do. You should go here, buddy. And you should go here. And then 3 units, 2 below. 3 units, 4 below. 3 units, 4 below. Yep, this is rounding out to look pretty good. And we come back and reach the axis halfway between those guys, every 1.5 squares. Here. So I mean the minimum and the maximum are separated by 3 squares. So halfway between there, we're coming back. And I guess the zeros are happening every half period, every pi by 2. So you just keep counting every 3 squares. A lot of cycles for this one. Putting my drawing skills to the test for sure. Maybe I'll make a little mental note too for this question, just to change the scale up a little bit. Because we're graphing way more cycles than we needed to. All right, nice. So again, guys, you guys can do this kind of question where you just have a graph and you can pick off the amplitude, the period, the phase shift, the axis. Those are all things you can read off of a graph. And so you can get the equation. You can build an equation just like we did here. All right, let's continue. So we're going to do a similar problem, but this time, this time the period was pi. But a lot of like real life processes don't have periods that are in terms of pi. Like a carousel might spin around every 2 minutes, or um, uh, or a ride at a fair might spin once every 5 seconds or something, right? So how do we deal with that when the period isn't a multiple of pi? So we're going to do something similar here. But yeah, this time the period and the phase shift aren't going to be multiples of pi. We're going to see it's just like we did last time. So let's pick some things off here. So amplitude of 2, and this time we're building a sine function. Guess I'm working in, I'm going to stick back to, I like my purple here. Amplitude of 2, period of 1, okay? So the period is 1, so what's k? K is equal to 2 pi divided by the period, which is 2 pi divided by 1. And so our value for k is actually going to be 2 pi. What's our phase shift? 0.5 to the left will correspond to a value for d of negative 0.5. And our axis, 3 units upwards, so our axis will be at y equals 3. And now we can sketch that. Draw in the axis. Okay, now that we know that since the period is 1, I'm going to just maybe let every 4 squares, you know what, the period's 1, that might actually be probably more cycles than we need. Period is 1, what will work out nice? I think if I make you guys can do what you like. I'm going to make every 8 ticks 1 unit. Yeah, I think that'll work out good. So that will be, and I'll maybe even add in, that'd be 0.5. Yeah, I think this will work well. That'll be 1.5, negative 0.5. Of course, when you guys are practicing at home, you guys can kind of make the scale that fits best for you. Negative 1.5 there, and then just a little bit off would be negative 2. That's okay. All right. So let's graph this guy. So the phase shift is 0.5 radians left, and we know that sine starts on the axes. So there's going to be our starting point. And we know the sine function starts there, goes up, comes back down, and hits the axis every half a period. Here, our period is 1. So every 0.5 units, we will be coming back, and we will be hitting the axis. So let's add in those points. I'll even add one more over here. Okay, and we know the sine function starts at our starting point, goes up and comes back down, and it goes up 2 above and 2 below the axis every halfway. So 2 above, 2 below, 2 above, 2 below, something like that. Oh, that last one's way off. Is this going to erase it all? Phew, didn't erase it all. When you guys are at home using pencil and paper, I'm under pressure here. I'm using my tablet pen. Okay. All right, pretty good. And let's get the equation actually. So our amplitude is 2. Sine. Our value for k was 2 pi. And then we have x. Our phase shift was 0.5 left, so plus 0.5 radians. And then our axis was plus 3. So what you guys are going to find is when you have a real life scenario and the period is like 5 seconds or 1 second, your k value is going to often be in terms of pi, kind of like here. All right, guys. In our last example, we're now going to kind of do one more similar thing. We're going to take some information and create a model. But this time, instead of just describing some transformations, we're going to actually take a theme park ride and we're going to model that. We're going to model our vertical height above and below the ground as we ride along this theme park. And so you guys have probably seen many rides, just basically just at a park spin you in a circle. A Ferris wheel is run where you're going up and down and up and down. You can model that with periodic function. This one's tilted at an angle, but you're still going up and down above the ground. You reach a highest point, a lowest point, a highest point, a lowest point. And so these are kind of natural for a modeling with a periodic function. So we have some information here. So we have the maximum height above the ground and the minimum height above the ground. So remember, we can find the amplitude and the axis using that maximum height and that minimum height. The wheel completes one turn in 5 seconds. That's going to give us information about the period. And the model predicts its highest point at t equals 0 seconds. So that's going to help us determine what a good phase shift would be. All right, so let's get started. So I've just got some space here. We will determine the values of A, K, C, and D. And this is kind of like the work I'd like you guys to show if I give you a scenario to model. But yeah, let's dive right in. So the A corresponds to the amplitude, and we can get this by doing the maximum y value minus the minimum y value and divided by 2. 7.5 is the highest, 1.5 is the lowest. You get 6, and that divided by 2 is 3. So no big surprise there. Many of you guys could probably have visualized that. So we've got our value for A for creating our equation. What's our value for K? So the period is 5 seconds here. So our value for K, remember K is always 2 pi divided by the period. In this case, it's 2 pi over 5, and that's fine. If you want to leave it as 2 pi over 5, we can write that as 0.4 times pi if you guys like. So we got K. Determine C. So where's the axis? So if you couldn't do the mental math about what halfway between the highest and lowest is, that's okay. Just find the average of the max and min values. Add them, divide by 2. Y min divided by 2. Nine divided by 2, 4.5. So we're going to find the phase shift in a second, but I wanted just to add some of this detail to our graph. So our axis, we know it's going to be at 4.5. All right. Now let's talk about the phase shift. So if you read our question, and hopefully you're fine with those three are kind of easy to pick off, to be honest. The phase shift is the more challenging one. So we are told that for our model, the highest point should be at t equals 0 seconds. So on our graph, we know our highest point at 7.5 meters is going to be right here. That is a point on our graph. Now, if you think about it, so the sine function doesn't start at a maximum. It starts on the axis. It would be actually very useful to model this scenario with a cosine function, and we'll give a cosine equation when we're done. But the question did ask here for a sine function model, so we have to ask ourselves what the phase shift is going to be so that we get our first maximum at 7.5. So there's several ways we can reason this out, but I'm going to just write a little blurb in here. Go down to 14. So let's talk about this. Let's talk what the phase shift is going to be. So I'm just going to type in here, the max value for sine usually occurs usually occurs at 1/4 of a period. I'm going to pause there and just go back to one of our graphs of the sine function. Here's one here. So that's actually cosine. So look at our dashed line here, guys. Maybe actually I'll just pull up Desmos. That would actually be easier. Inspiration. So sine x. The period of the sine function, don't even worry about what the period is. I know it's the 2 pi, but where does the first maximum occur? The first maximum always occurs 1/4 of the way through the period, because you do at 1/4 you're at a max, and another quarter you're back to the axis, and another quarter you're at a min, and another quarter you're back to where you started with. So the first maximum will occur 1/4 of the way through the period. What's 1/4 of the way through our period in this question? So the max value for sine normally occurs at 1/4 of a period. And so in this case, 1/4 of a period is 5 divided by 4, which is 1.25 seconds. So so normally what we would expect to see is our maximum. I'm just going to draw this in there. Normally, we'd have a maximum at 1.25 seconds. For a normal sine function, it would start on the axis and it would go up here. Ours doesn't start there. Ours starts at 0. So what's the phase shift? Well, we can visually see what it is, right? For our graph, we need to take the sine function and we need to shift it to the left, for you guys, to the left by 1.25 seconds. So we can see the phase shift. It's left 1.25 seconds. D is equal to negative 2.5. But we can get that mathematically in the following way. We know that the difference, we know for our phase shift, that phase shift difference has to be 1.25 seconds. And our value for t, we're going to sub in here, is the value where we have that maximum, 0 minus d equals 1.25 seconds, right? 1.25 corresponds to our first max, right? The first max, like where it should be. Well, in our graph, it has to be at 0. So what's the difference? If you solve that equation, you get d equals negative 1.25, which is exactly what we just talked about. So we've got everything. Let's make the equation. Let's graph it. And then maybe we'll check this one in Desmos. So our amplitude 3, we are doing a sine function. Our value for k, 0.4 times pi. Our phase shift, arguably the most challenging thing to find. We reasoned it out. 1.25 seconds to the left. Close the bracket. And our axis, 4.5. And we've got it. Let's make a graph. Let's check it in Desmos afterwards. Okay, so we know we start there. And our period is 5 seconds. So every 5 seconds, we're just coming back to that maximum after 10 and after 15. Where are we going to hit a minimum? We're going to be hitting a minimum halfway. And that's at 1.5. So halfway, 1.5, halfway, 1.5, halfway, 1.5, something like so. And then we hit the axis halfway between the max and mins. So here, 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 and it would be here. Okay, so we start at the top, and then our ride goes down. As we keep spinning, as the ride keeps spinning round and round, we go up, we go down, we go up, we go down, etc., etc. Now I'm going to pop this into Desmos, and let's check this one out. So I might just change my graph settings just back to just a normal. So for our x, I think we went from -1 to around 16. And for our y's, we'll just go from like -1 to 10 or so. That should show things pretty well. We're done with u. And yeah, we think our graph is this. Y equals, the amplitude was 3 times sine, bracket, 0.4 times pi, bracket. Phase shift was 5/4. That should be plus 1.25. And then our axis, close that bracket, was plus 3.5. 7.5, 1.5. What was our axis. Our axis was 4.5, excuse me. That's why it wasn't lining up. All right. So yeah, we start at a maximum. We repeat every 5 seconds, going up, coming back down, lowest point 1.5. Everything seems to fit. I think we did a good job. All right, last thing I want to do, arguably it would have been easier, and this is just good practice in general. Often we model our periodic functions with a sine function. Cosine functions work just as well. And because this guy started off with this with a maximum, an alternate equation would be using cosine, same amplitude, but cosine. And in this case, you have I used D there, and I should have used T. Please forgive me, guys. The period's still 5, so our k value is still 0.4 pi. However, there's no phase shift with this when we use the cosine, because cosine's supposed to start at a maximum, and then the axis is the same. And if for the last thing I do, guys, I'll just plug this into Desmos as well. 3 times cosine 0.4 times pi times x, and then plus 4.5. You can see you get the exact same function. All right. So yeah, pretty neat. Let's kind of summarize what we should be able to do after today. And what we have done. So we reviewed the different transformations and the properties they affect for periodic functions. We reviewed, got some more experience graphing transformations of periodic functions using, in this case, the period in radians. We graphed some sine functions. We graphed some cosine functions. We talked about how to model a situation with an equation and how to find the axis, phase shift, period, amplitude. You guys should be able to do this with either information or just from a graph, picking off these properties. And then we modeled a real life situation, and we talked about how to find the amplitude and the axis by using the max and min values, how to find the k value using the period, and we talked about how to reason out a phase shift. And so you guys should be able to model any periodic behavior as long as you have information about the max and min value, the period, and some kind of starting point where you can reason out a phase shift. So as usual, guys, I've got some suggested practice for you. I also will have a short assignment, making a few graphs, coming up with a few equations, and modeling a real life scenario with a periodic function. All right, so that's it from me. Hope you guys enjoyed the lesson. Hope you're staying well, and we'll see you soon.